Thinking in C, Chapter 7, Pointers 101. A pointer is a variable that contains the address of some other place in memory. It's a way of referring to memory storage locations indirectly. And so the technique of using pointers is called indirection. That's what we're going to talk about. And in addition to that, we will use pointers to simulate call by reference as opposed to call by value. Another thing you can do with command line programs is to look at the arguments that are passed when you invoke the program from the command line. And that's done through pointers, so we'll cover that. And then we'll also cover the heap, dynamic memory. Before we actually get started, I'd like to make it clear that for those of you that are going on to Java, you don't really need to know every little thing we're talking about here. You're not going to be doing explicit indirection in your Java programs, as you'll find out. But you still need to understand the concept of indirection because it's used in Java. It's just implicit, that's all. So by going through this section, you'll still get the concepts down that you need. But don't worry about the syntax. You won't need it when you get to Java. A pointer is somewhat like an integer in that it holds a number. But the number that it holds represents an address where something else is stored. And you go indirectly through the pointer to get at that other object. When you declare a pointer, you don't just say, hey, this is a pointer. It always has to specify what you're pointing at, that is, what type of thing. So, you'll have a pointer to an int, or a pointer to a char, or a pointer to some other struct or whatever. You can point to anything. But the point is, that when you declare a pointer, you have to say what it's pointing at. All right, well, why are we doing this? Why do we use pointers anyway? Well, the main reason we use pointers is for dynamic objects. That is, for variables that you don't know about ahead of time at compile time. In other words, you create them at runtime, you don't know how many you're going to have, and so you have to get them from somewhere. You can't put them on the stack because that's where local variables go. They can't go into static storage because that's where your global variables and your other static variables go. So there's a separate concept of memory, and that is dynamic memory, and we usually call that the heap. In C++, it's sometimes called the free store. Another use for pointers, in addition to dynamic memory, is when you want to actually query or insert a value at a certain memory address. I'm not going to give any examples of this, but mapped memory, if you're familiar with that. Mapped memory is memory that's mapped to some device, and so whenever you put objects in certain locations in that mapped memory, then things will happen on the device that it's mapped to. That's another use for pointers, and again, that underscores the use of C as a systems programming language. Accessing an object through the pointer that is pointing to it is called indirection, as I already mentioned, and there are two operators in the language that help with this. First, we need to have a way of getting the address of an object so we can store it in a pointer. And one way we do that is we use the ampersand operator in front of some variable. That gives you its address. The other way, as you'll see in a little while, is we have a special function that we call that allocates something on the heap, and it automatically returns the address for you. To go the other way, that is to do the indirection, going through the pointer to access the variable that you're pointing at, you use the star operator as a unary operator on the pointer. This example illustrates the two pointer-related operators as well as a pointer-related format specifier for the printf statement. What I'm doing here is I'm declaring an integer I, initializing it to 7, and then I declare IP to be a pointer to an integer. That's the role of the asterisk in the declaration. So IP is a pointer to an integer. It is initialized with the address of I. So I holds a 7, IP holds an address which happens to be the place in memory where I is located. So we have two ways of getting at that memory. One is, of course, just referencing the variable I. And another would be to indirectly go through the pointer variable IP. So we can do that here. First, I'll print out the pointer itself, and that is with the %p format specifier. Whenever you see a %p, you'll know that it's going to print the corresponding argument to printf as an address, and most platforms print that as a hexadecimal number. And then the next argument is *IP, and that's an integer. Since IP is a pointer to an integer, then the contents that it's pointing at, *IP, is an integer. Now, I can actually change what is in that location, as I said, in two ways. I could use I could say I equals 8, for example, but I can also go through the pointer. So in the next line, I'm saying *IP equals 8. And to show you that that actually makes the change, then I'm going to print out again what is in the contents of the address that IP is pointing to, and you can see it now contains an 8. And if you were to print out I, you would also see that it's an 8, because it's the same place in memory. This slide is just a visual on what's happening. I is at some address in memory. Normally you don't know what that address is, and you don't care. But in this particular example, it just happened to be at the location 0012FF88. And in IP, I store the address of I, so that means that IP has that number, that particular address, as its contents. And when I take *IP, that operation means go over to the location referred to by IP and look at the contents there. So that's what was happening in the example on the previous slide. Since we have a way now of indirectly getting at another memory location through a pointer, what we can do now is simulate what we call reference semantics. Recall that all functions in C pass their arguments by value. That means a copy is made, and so if you make any changes to that formal parameter value in a function, it makes no difference whatsoever on the original argument because a copy was sent to the function. Well, if you want to have reference semantics, you can do it kind of coming in the back door. What you can do is, instead of passing a value, pass a pointer, pass the address of something. And then in your function, you receive that address as a pointer, and then you can go through that pointer and make a change at whatever memory location you're wanting to make a change at. So it's really kind of a simulation of reference semantics. You have to do it through pointers. You don't have direct support in the C language, but the interesting thing is that C++ does support it. C++ has what we call reference parameters. They have a thing called a reference. But C doesn't, and interestingly enough, neither does Java. This example shows you how to do reference semantics with a function. The swap function that I'm writing here, notice that it takes pointers. It takes x, which is a pointer to an int, and y, which is a pointer to an int. And it's going to swap the contents that those things are pointing at by doing the usual algorithm. It'll store the contents that x is pointing at in the int temp. And then it'll take the contents y is pointing at and assign it to be the contents where x is pointing at. So notice that the indirection operator can be on the left-hand side of an assignment statement. So it just does the right thing. It knows that what you mean to do is to alter the contents at that address. And then, of course, you do the last operation, which is to put your temporary in the y slot there. So the main program is going to call swap, and notice what it does. I have a couple of variables, I and j, and I actually want to swap them. Well, I call swap with the address of I and the address of j as arguments. So those are pointers. Addresses are pointers. It's that simple. So swap does the right thing, and when I print out I and j, you can see that, yep, they did get swapped. The concept of ragged arrays is a way of using pointers to conserve memory. The idea is this. Imagine that I want to have, say, for example, an array of strings, which in C, as you know, is an array of char, array of characters. Well, if I wanted to have an array of strings, then I would have to have an array of characters. That's fine, but that means I basically have to have a two-dimensional array. But since strings tend to be variable length, of course, what I'm going to end up with is a lot of wasted space if I store a bunch of strings in a fixed size two-dimensional array. the size of the rows is going to have to be the maximum for whatever my longest string will be. And if any of my other strings are shorter, by virtue of having a terminating null somewhere in the middle of the array, well, then I've got all this other space left out on the right-hand side of each row that's not being used. So to get around that, one thing that's commonly done in C is to allocate instead an array of pointers to char. And that's what that vertical vector on the left is meant to represent there. It's an array of pointers, and each of those pointers is going to contain the address of where the actual array of characters begins, which will be each string in the list. So the way this is usually done is we'll declare an array of pointers to character and then go through and allocate dynamically at runtime the memory that you need. And I'll show you how to do that in a few slides. That's this dynamic memory that we're talking about. And then copy into each dynamic memory segment the strings that you're interested in processing. Turns out that the C runtime system gives you a ragged array of strings which represents the command line arguments you can type on the command line when you invoke your program. The way you get them into your program is by using arguments to main. Up until now we haven't used them, so there are really two different ways of writing the main function. One is without any arguments, and the other one is with these particular two types of arguments. An int as the first argument, and an array of pointer to character as the second argument. Now the names argc and argv, of course, it's not important what name you use, as you know, because when you write a function you can name the parameters to be whatever you want. Just so you know, though, those names are pretty entrenched. They were in the original book by Kernahan and Ritchie, written in 1978 or 76, whenever it was. And everybody's used it ever since then. So I'm not going to break tradition. I'm going to use it as well. Anyway, that second parameter, argv, it is a ragged array. It is an array of pointers to character, and the runtime system has each of those pointers pointing to your command line arguments, and the memory is allocated dynamically so that it doesn't take up more space than you need. This example uses arguments to main and shows you how to actually use them in your program. It's quite simple. Again, you just declare those arguments, an int and an array to pointers to character, and then you just use it. For example, I can have a loop that goes through and prints them all out. So I'll have a for loop, which goes from 0 up through but not including argc. Argc is the number of arguments. I guess I forgot to make that clear on the previous slide, but it stands for argument count. Argv stands for argument vector. And for each of those, I will just send them as an argument to put s. Put s prints out strings. And so argv sub I is a string. Now, at the moment, you're probably a little confused. You're thinking, now wait a minute. You're telling me it's a string, but argv sub I is really a pointer to character. Well, I will unravel that mystery as the next few slides unfold. It turns out that the name of an array is just a pointer when you pass it to a function anyway. I think I actually mentioned that in a previous chapter, but now we're going to really learn what's going on here. Anyway, notice the output. It's interesting. What I'm typing in for my two parameters are hello and there. And the name of the program is Eckel. If you'll notice, the comment there had echo.c. You're probably wondering why I have the dot backslash there. This is in DOS, by the way. Well, the reason for that is because echo is a built-in command in DOS, and so it won't run my program if I just type echo. But if I type ./echo, that tells the system to load the program in the current directory named echo. And notice that I get 3 strings as output. I get a full path name, d:\tic, that's the name of the directory that I had all this stuff in, \echo.exe. That is the full file name of the executable file on my DOS platform. And so that is the first command line parameter. So the program name is also passed to you inside of your program itself. That's a nice feature. And then the next two, of course, are hello and there. In the examples that follow, we're going to be using a special constant pointer value named null. So I thought I'd better explain it now. It's a special value, and it really doesn't represent any address. You can think of it as the address 0, although numerically it doesn't have to be 0. Nonetheless, it behaves that way, meaning that it's an invalid address. You're not allowed to point there, not allowed to use it. The only reason we use null is for comparison to other pointers, and so we use it as a flag in certain instances to indicate that we do not have a valid pointer. For example, some functions will return null to let you know that the function failed to do what it was supposed to do, or that it hit end of file, depending on the function. So just keep in mind that you can't dereference null because it's not a valid pointer. It's strictly used for comparison purposes. Well, now we can talk about using dynamic memory, about how to allocate memory yourself, and in particular, how to create your own ragged arrays to save memory. The way you ask for memory on the heap is you call a function named malloc, which I suppose stands for memory allocator, and you pass it the number of bytes that you want. So if you want to put an int on the heap, you have to pass it a size of an int, and then it'll give you back a pointer to wherever it allocated that memory, and you just use that pointer to indirectly work with that space. As I mentioned on the previous slide, some functions return null when things go wrong, and this is one of them. If for some reason memory fails, there's not enough, which can happen, malloc will return a null, and that's how you know that things didn't work. It's important that when you're finished with the memory, that you give it back. And this is really common in programs where you create and destroy objects quite dynamically. I guess one example of that would be a program that uses some of the data structures that you're used to from previous experience in, say, college or in complicated programs. Data structures such as lists, linked lists, queues, trees, things like that. All of those dynamic data structures are such that you always have objects come and go all the time. And if you don't release your memory back to the heap when you're finished with it, well, you're going to run out of memory a lot sooner than you want to. So always remember to do that, and you do that by calling the function free. You simply pass as a parameter the pointer that you got back from malloc earlier as an argument to free. C actually has 4 functions to manage the heap, and here are their prototypes. You can see that malloc takes a parameter of a very strange type, which you haven't seen yet. It's called size t. Well, it's really just an unsigned integer. Size t is defined usually as an unsigned int. And that makes sense because you don't expect to have a negative number of bytes that you want to request. But just think of it now as an integer if you like, because we really haven't talked about unsigned integers very much. Notice that malloc returns a void pointer. Malloc is a function that takes a size t argument and returns a pointer to void. Well, now that's an interesting concept. What does that mean? Well, we're really not going to get to that in detail until the next chapter, and so you really only need to worry about that if you're going on to C++. But basically, it means a generic pointer. Remember that to use a pointer, it has to be a pointer to a certain type, an int or a structure object or whatever. The system needs to know how big your object is that you're pointing to, otherwise you can't do anything with it. Well, malloc doesn't really care how you're going to interpret the memory you get back. That's your business. And so we need some kind of generic way of saying, well, it's a pointer. And that is called void star. So any pointer can be represented as a void star, but you need to store it into a pointer of the correct type before you can actually use it. You'll see this in the next example. Free, as I mentioned, is the function that you use to return the memory to the heap, and that's done by just passing the pointer as an argument. There are 2 more functions that come in handy. One is calloc, or sometimes pronounced calloc. It takes 2 arguments, and what those arguments do is define an array. You use calloc to allocate an array on the heap. The first argument is an integer that is the number of elements you want in the array, and the second argument is the size of each element. So basically the system is just going to multiply those two numbers and give you that many bytes back, give you a pointer to that many bytes back. Realloc is a very useful function. It takes a pointer that you already have allocated on the heap, whether it was from malloc or calloc, doesn't matter, and it basically reallocates it so it can grow. That's what you usually do anyway, is you do a realloc so it can get bigger. You could give it a smaller argument if you want. But what happens is if you give it an argument of a certain size, and if there's enough memory to expand that area without moving it, then everything will just stay right there, which is nice, and you'll just expand and use whatever the empty space was at the end of your previous array. If there's not, then it'll be copied to a whole new area. So it's a pretty nice function. It makes it so you don't have to do that yourself. You don't have to malloc a new area, copy things over that you have already used, and then of course you'll leave the rest of the unused space alone until you initialize it later. Anyway, realloc does that all for you. This example, which occupies 2 slides, shows how to use malloc and free to build a ragged array. Notice that I'm including standardlib.h in my second include line there. That's where the prototypes for the heap functions are defined. You always have to include that if you're going to use malloc or its associates. String.h is there because I'll be doing some string operations. Again, a ragged array usually makes sense only when you use characters. Of course, you can always do it, but it's most commonly when you have arrays of characters representing strings. So the first variable that I declare inside of my main function, lines, is an array of so many pointers to character. That number, of course, is defined a couple of lines above. Max lines is 100. So I'm going to allow up to 100 lines in this array. What I'm going to have to do, though, is I'm going to have to read a line at a time, then allocate the memory on the heap for that line, copy it over to that heap space, and then just continue on in that fashion. So I need a buffer to read each line in one at a time, and so that buffer is going to be what I call line, and it can hold up to 80 characters. Remember, you always have to leave one for the terminating null, and so that's why it's 81. Well, to fill the ragged array, all I have to do is read a line at a time until I run out, and then allocate the space and copy it over. So that's what this loop does. I have the variable n starting at 0, and then while n is less than max lines, which means while I have room in my array for another one, and while I consumed another input line, that's the function getS, it reads an entire line up to and including a new line character. It throws away the new line character and puts everything else into the character array that you gave it as an argument, and then appends a terminating null, so it's a valid C string. If you ran out of input, in other words, if you hit into file, then it returns a null. So while there was room in the array and while I got a string, I will execute the body of the loop, which begins with the if statement there after the curly brace. Now what I'm doing in that if statement is I'm calling malloc, asking for enough space to store the line that I just read plus 1 for the terminating null. Remember, the strlen function does not count the terminating null in its computation of the length of the string. So I'll allocate that on the heap. Malloc will return me a pointer. I'll store that right into the next open slot in my array of pointers. And then after that assignment is made, notice that I have that assignment in parentheses, that will be compared to null. If it is null, that means that the memory failed. That means that malloc returned null. And in this case, I'm just going to be lazy and quit the program. Exit is a function you haven't seen yet. It's defined in standardlib.h. And it uses the same conventions for return values as returning from main. I'm returning a non-zero to indicate that there was an error. If, however, there was enough memory, that won't happen. I'll skip down to the next line, and that's stir copy. I'll just copy my second argument, which is the buffer that I read into. I'll copy that into the area on the heap. Now, again, there may be something that isn't crystal clear to you for now. You've seen stir copy before, you've seen put S before, and up until now, we have been just giving them strings, either literal quoted strings or names of arrays. Well, again, the reason that this all works is because the name of an array is just a pointer, and a quoted string literal is also just a pointer. When you type in a quoted string literal in double quotes, the system will allocate space for that, put those characters in there, and then return the pointer where it put it. That's just the way it works. So all of these functions that we have been passing strings to, they really just take pointers. And if you want to prove that to yourself, why don't you just open up string.h in your programming editor and look at the prototype for stir copy. You will see that its first parameter is of type char star, and its second parameter is of type const char star. You can ignore the const part for now. We don't cover that until chapter 8b. But that is just telling you that it's taking pointer arguments. Here's the rest of that sample program. Now that I have filled the ragged array, in other words, I've stored in each pointer element in the array the address of the memory that I allocated on the heap and copied a string into, well, for each of those now I want to print them out. So I'll just have a loop that goes through however many I read in and call put S on those. And actually I'm going to print them out in reverse order just for fun. Notice that after I print each line, I will return its memory to the heap by calling free. In a program like this, it doesn't make a whole lot of difference. Most operating systems will free up any space that was used by a program when it exits, but it's just a good habit to get into, to always free any memory that you allocate. Since you need to give the size of the objects that you want to allocate on a heap to the malloc function, or to its relative functions like realloc and calloc, you'll be happy to know that there is a size of operator, which is pretty handy. What it does is it gives you the number of bytes in its argument. Now, it is an operator, although most people write it as if it were a function. Well, that's okay. Extra parentheses doesn't hurt anything. But it's an operator, a unary operator. So what you do is you write size of, and you follow that by the object that you want the size of. That's one of the uses of size of. The key feature is that it is a compile time operator. It gives you the size of the variable at compile time. So it's not something that you can find the length of a string with, and that's why we have the string length function. It turns out that there is a very nice idiom for finding the number of elements in an array. That's just taking the size of the array. So in the example I have here, assume that A is an array of some type. You take size of A and divide it by size of the first element. There's always a 0th element in every array. So you might as well pick A sub 0 as your element, and that quotient gives you the number of elements in the array. Another usage of size of is to find the size of a type instead of a variable. In that case, you do have to use parentheses. You can't say size of space float. That only works for variables. From here on out, we're going to be seeing a lot of struct objects on the heap, so we need to talk about that. It's not terribly unusual, though. In order to allocate an object on the heap of a struct type, you just use size of, as I showed you in the last example. So, for example, if I wanted to allocate an employee object on the heap, I would do like I'm doing here. I would call malloc and give it the size of struct employee. When you get one of those objects back, of course, as you know, you're getting a pointer back. And so the question is, how do you access the members of that structure? Well, you do it the normal way. You have a pointer, right? And so if you want to get at the struct that pointer is pointing to, you use indirection. So star P, in this case, is the structure. Now, if you want to get at the member of the structure, you have to use the dot operator. So dot member name.
It turns out that the dot operator is a higher priority than the indirection operator.
And so you've got to put parentheses around the star P so that that binds first. And since that's kind of a hassle, there's a shorthand for getting at a member of a structure through a pointer to a structure, and that's using the right arrow. You actually type out two characters there, the dash or minus sign and the greater than sign. That together is that token that means go through the pointer and get at the member of the structure that that pointer is pointing to. We haven't talked about how to pass structs as arguments. Of course, there's really nothing new to talk about as far as concepts go because you already know how to pass arguments. You've seen two ways. One is just to pass them. That is, they get passed by value because of the value semantics of the C language. But think for a moment. Let's suppose I have a struct and it's got a lot of stuff in it. Even these little employee objects we're talking about are sufficiently large that you might want to think twice about passing those by value every time you call a function that expects arguments of struct employee. So what you usually do is you pass a struct's address. So in other words, you'd use this reference semantics workaround that you can use in C. So that'll save the time and the stack space of passing an entire struct to that function. It's important that we talk about that for a minute because for those of you going on to Java, that's just what Java does for you transparently. In Java, it never passes an object by value. It always passes the address of that object, but it does it in a way that you don't have to worry about the pointer semantics. So the example on the next slide will show you how we do it in C, so just keep in mind that this is what is happening behind the scenes in a Java program. In this example, I have a date struct, which just has 3 ints in it for year, month, and day. Now that's not terribly large, but still it's larger than a pointer would be. 3 ints is certainly larger than a pointer. So I'm going to define a print date function which takes a pointer to a date struct instead of a date struct by value. So inside of print date, I'll use that special shorthand syntax for accessing a member of a structure through a pointer. So I have P points to month, P points to day, P points to year. We usually pronounce that P arrow month. It's a little easier to say. And in the main program, as you would expect, I simply pass the address of the date struct object, D. So print date ampersand D. Now we can finally clear up the issues having to do with arrays. Imagine passing an array as an argument. It's the same reasoning that we just went through with structures. You don't want to pass an entire array by value. That would be very inefficient. Now with structs, you have a choice, of course. You can pass it by value if you like, or just pass an address to it. With arrays, you don't have a choice. You cannot pass an array by value. In other words, an array is not really a first-class object in C. Arrays are kind of special. What happens is when you pass an array as an argument to a function, automatically, instead, a pointer to the first element of that array is passed. So what that means is when you write your function, the parameter that is going to receive that pointer can be written as either a pointer or as an array with empty brackets. So for example, if I had a function to which I would pass a string, well, a string, of course, is an array of characters, and so a pointer to the first character is going to be passed. Well, then I could write the parameter for that function as either a char star or a char array. Either way, they mean the same thing when you use them in the context of a function parameter. This exercise is a variation on the employee example that you've been working with. The main change we want to make here is we want to have employee objects on the heap. This allows you to create them dynamically. And once again, I'm going to give you a header file which has the declarations of all the functions that I want you to implement. So on the next slide, you'll see that. They're all pretty self-explanatory. And a key new function that you need to create is called createEmployee. What it does is it takes as arguments the various data elements that are going to be the members of employee structure, the last name, the first name, the title, the salary. And then it will allocate a new employee object on the heap and return a pointer to that new object. So if you'll take a look on the next slide, you'll see the declarations for the functions for this exercise. You'll see something a little new in this header. You notice that it begins with some preprocessor directives, one of which I don't think we've seen yet. If in def, that stands for if not defined. The way the preprocessor works as far as these symbols go is when you define something, it's entered into a special symbol table that the preprocessor maintains. And once something is defined, it knows whether it's defined or not. Even in this case, we don't even care what the value is. We just want to know if it's defined. And so what you're seeing here is a common idiom to make sure that header files are only included once in a compilation. So what happens is the first time this header is encountered in a compilation, well, the symbol employee_h, which I just made up to match the file name, will not have been defined. So what we're going to do is define it, but now skip all the way down to the bottom of the file and you'll see a #endif. It's important that every if or variation of an if in the preprocessor is matched by an endif. So everything in between the if not defined and the #endif will be included the first time only. And then if for some reason this header file gets included through some other inclusion path in the very same compilation, well, employee_h will already have been defined, and so you won't have the problem of duplicate definitions. Well, anyway, here it is. The struct employee is pretty much what you've seen so far. And what we have is a function createEmployee, as I explained in the previous slide. That's the one that creates a new employee and gives you a pointer back. And now notice that all of the rest of the functions take a pointer to an employee struct. And that's obviously because you need to pass the pointer to the struct that you're using to operate on it. And that's pretty much how that works. And believe it or not, this little exercise is a good introduction to how classes and objects work in C++ and even in Java. The test program for this exercise is on this slide and the next. I'll just let you take a look at that. There's not too much to say. Just notice that there's an array of pointers to employee structs. I'll create a couple of them and store them on the array. At the top of this slide, I'm creating an empty employee. That may not be the way you would normally do it, but I just wanted to show you that I can use those other functions which set the members, set last, set first, etc. It's an alternative way to what I did on the previous slide of providing all of the initialization information in the call to create employee. Well, you are at the end of the main part of the course. Here's where we part ways. If you're going on to Java, well, there's nothing else for you to learn other than to take a look at Java just to get the overview. And so that's in the Java section. Just go to the root of the CD and look for the Java intro presentation. And that'll be it for you. If you're going on to C++, though, there still is another one to do. And so you'll see a CPP prep presentation on the root of the CD. And that's the one that you need to look at. And it has the chapter 8b, which has more on pointers, and also the first look at C++. Congratulations.